Good afternoon. Good afternoon, everyone. Let's wait for a couple of minutes. We will start then. Let everyone join. Is my screen visible?
Yes.
Okay. Okay, I think we can start now. Others will join in the meantime. Let me first introduce myself. I am Ananya. I'm currently doing PhD in IIT Kanpur, and my specialization is microelectronics and MVLSI. I'll be your TA for this session. So, a couple of announcements I want to make before starting the session. So, I can see number of participants here is 8, so that is including me. So, there are not many participants. So, you can unmute yourself and speak if you have any doubt in between. So the format will be, I'll try to solve some of the questions. I'll give you the questions first and you should try yourself first, and then we can discuss if there is any doubt. And once the discussion is over, then you can ask me about the questions or any doubts that you have for this week. Also, I am recording this session. It is mandatory to record this session, so I'm informing you beforehand. Another announcement is that for this meeting, this will be for 2 hours till 5 o'clock. So I'm using my personal ID. If any case the meeting cannot exceed up to like more than 60 minutes, then I will share another link. Please join using that link for the second part. I mean, if this meeting ends after 60 minutes, and please remind me if I forget to share the link maybe within 40-45 minutes or so. Okay, so since there are not many people in this meeting, so can you please tell me like what you are doing currently, whether you are in UZ, PZ or PhD or working somewhere. You can write in the chat box or unmute and speak. You can just type your current role or what course you are enrolled in the chat box. Okay, I'm not getting any answers here. Okay. Okay. Okay, so since most of you are PhD students or doing masters, so some of the topics those were covered in the week 1, so you must have studied earlier also. MTech in power electronics. Okay, so let me discuss some of the questions from week 1 syllabus. So this will be mainly problem solving session, so I'll not discuss much theory but mainly focus on the practice problems. So what were the topics covered in the first week, if you can tell me? Like first topic was why silicon is used and fundamentals of IC fabrication technology, and what other topics those were covered? Okay, mainly in the week 1, crystal structure, Miller indices, and all those topics were covered. So the questions that those I have prepared, those will be from those lectures only. So let's start first, and please solve the questions along with myself. Like, I'll share the problem first and then you can solve it by yourself. Okay, so this is the first question. What is the primary reason for dominance of silicon in semiconductor device technology? So this was covered in the very first lecture. So, please tell me the answer first. You can unmute and speak because I'm in the presentation mode. It will be difficult for me to go to the Google Meet link again. Okay, I'll wait for some time, but you should give me the answer because otherwise this session will not be very interactive. And please try to make it interactive.
Option C, ma.
Option C. Okay, favorable properties of silicon dioxide. So, why you are selecting that? Can you please explain a little bit more? Your option is correct. It is the answer C, favorable properties of silicon dioxide. But what was the reason, if you can recall?
Like while at the time of oxidation, it will not create uh, like any uh,
Okay, so let me help you. So,
yeah.
in any material, in the top part, the top layer,
Yes, ma'am. The
there.
top will like kind of it reacts with the environmental like air or water,
Mhm.
but wherein in silicon material itself, it is kind of uh,
It goes into
I'm not getting the
oxidation. Like
right
at
word.
the top part, there will be an oxide layer, formation of oxide layer. That will be
But
silicon
when we
dioxide.
connect the gate, the other different material, it'll like collide without making any gap or like air gap or something like that.
Okay, so there will be dangling bonds in any material at the top part. So in case of silicon, the top surface is passivated because of the formation of silicon dioxide layer. And this silicon and silicon dioxide interface, uh, it is very well known and well studied. So there will not be any dangling bonds or any other kind of material, other kind of atoms. And also the silicon dioxide layer, that silicon dioxide interface, that is used in MOSFET also. You know that MOSFET is the basic device that is used in integrated circuits. So because of this native oxide, so silicon dioxide layer, so and the properties of silicon dioxide, it is very useful. So that is why silicon is mostly used, almost in used in semiconductor device technology. Okay, and what about the other options, like what about the first option, abundance of silicon on the surface of the earth? Okay, so this is also one reason, one of, not one of the main reasons, but silicon is can be silicon wafers are made from silica, so which is sand, uh, but it involves a lot of processing and other techniques, and those techniques are also well developed. So that is why also uh, it is why silicon is used mostly in semiconductor devices. And what about the band gap properties? Do you know what is the band gap of silicon, and what type of material, what kind of band gap is there in silicon? What is the band gap of silicon in room temperature, say?
1.12 electron volt.
Yes, it is 1.12 electron volt, and silicon is an indirect band gap semiconductor. So, indirect band gap semiconductors are not useful in some applications. So, for those applications, direct band gap semiconductors are used. For example, gallium arsenide. So, that is a direct band gap semiconductor. So, for some applications, silicon is not used. So, that is the second option. And the fourth option is lower melting point. So it is not correct. Silicon has melting point around 1400 degree centigrade. So the most appropriate answer is this C. Okay. Okay, so this is the next question. There are two identical photolithography systems, and there are two light sources. System 1 has a light source of wavelength 160 nanometer, and system 2 has a light source of 320 nanometer. So what is the relation between the minimum feature sizes for these systems? So what do you think it is? Which one is the correct option? So I'm giving you 1 minute. Just think about it and let me know the answer. If you don't want to speak, then you can write in the chat box also. I can check that, maybe can come out from the presentation mode and I'll check. Okay, so these were for the last answer only. For this question, okay, let me show the question again. So what is the answer? Is there any answer here? Okay, so the answer is C. Minimum feature size for the first system is less than the second system. So is there any confusion in this question? This was also covered in one of the lectures. Okay, since there is no option, I think it is clear. Let's go to the third question. So consider a free electron moving with a velocity. The velocity is given as 1 by 30 to c. C is speed of light. So what will be the de Broglie wavelength for this electron? So please calculate this and give me the answer in the chat box. So I'll wait for 2 minutes. So I am also solving along with you. I'll wait till you give me the answer. Okay. So this is the formula. If you don't remember the formula now, then you can use this formula and calculate and tell me the answer.
Ma'am, option D.
Option D. Okay. Anyone else? Okay, so option D is correct. Here you should be careful with the units. So what is the unit? H is here Planck's constant, right? H is Planck's constant and its unit is joule second. So you should check whether you are getting the right unit or not. Joule in MK system, what will be its conversion in MK system? How we can write joule as? Can someone tell me?
Kilogram meter square per second square.
Per second square. Okay. So let me write here. So this is kg. Meter square and second per second. Right? Because it is joule second, right? And then here kg and meter per second. So ultimately we will get
It should
meter.
be kilogram meter square per second square.
Yes, per second square, then one more second here.
Yeah, sure.
So that is why I have written as meter square per second. So the final unit will be in meter. So you should always check the unit, because in this course some units will be in meter and then some will be units will be in centimeter. For example, concentration of electron. So that N we generally write as atoms per or electrons per or holes per centimeter cube. So always check the unit. Okay. So let's go to the next question. So this is the question. Since some of you are calculating with me and giving me the answer, so I'll wait again for some time in this question also. You can calculate and give me the answer. So this is the question for hydrogen atom. So do you remember the formula for energy of an electron in hydrogen atom, or should I give you the formula at least?
I think it is minus 13.6 over n square in electron volt.
Yes, yes. So yeah, that is in electron volts. So the options are given in joules, so we should do the conversion.
Option A.
Option A 1.6. Yes, okay. So what about others? Others got the answer, or? So this is the formula, minus 13.6 by n square, that is in electron volt, and this is the formula for conversion because the answer is given in joule. So E2 and E1 values are this. Everybody got the answer? Right. Okay, I hope there is no confusion. Cindy. Okay, so yeah, it will be better if you unmute yourself and speak. It is difficult for me to see the chat box every time. Okay. Okay, so let's go to the next question if there is no doubts here. Okay. So this is the next question. This is on density in diamond lattice. So take a material X, that crystal structure of X is diamond lattice, and it has a lattice constant A equal to 0.6 nanometer. What is the density of this material in gram per centimeter cube? The atomic mass of the material is given and Avogadro's number is given. So calculate the density and tell me the answer. So I'll again wait for few minutes here. And if you don't remember any equations or formula, then you can tell me. I'll share that. And please be careful here with the units because the final answer will be in gram per centimeter cube, and the options are given in this unit only. So from lattice constant, that is given in nanometers, so use the correct unit. So what do you think, how we should proceed? Like how to start solve this question?
I think first we need to know how many atoms are there in diamond lattice, and then uh, finding the next like density by dividing that atomic mass by Avogadro number multiplied by number of atoms by that is constant Q.
Yes, okay, so first we should
Option
know.
B
uh, is someone is stating something? Yeah.
is the correct option. Option B.
Yes, the option B. So how did you come up? Like what are the steps you followed, so that everyone else also can follow and get the answer? Because the session will not be useful if everyone does not solve by themselves, right? So what are the steps that you followed?
The expression to calculate the density is number of atom per unit cell multiplied by atomic weight divided by Avogadro number into lattice constant Q. So the number of atom in a uh, diamond unit cell is 8. Atomic weight is given 30 gram per mole, and the Avogadro number 6.6022 10 to power 23, and the lattice constant is 0.6 into 10 to power minus 9. I have been calculated the question in kilogram per meter cube, and then converted into gram per centimeter cube.
Okay, okay, that is correct. So let me explain for others also. So the steps will be, first we should know a number of atoms per unit cell. So how it is calculated? This is unit cell for the diamond lattice. So there are 8 corner atoms, and these 8 corner atoms are shared by 8 cells. So the contribution for one cell will be 1 by 8, and there are 8 corner atoms. Then there are 6 atoms at the faces. So these 6 atoms, and these 6 were uh, shared between 2 cells. Like for this atom, this will be shared between this unit cell and the top unit cell. So the contribution is half, and there are 6 faces. And then there are 4 atoms inside this lattice. So these 4. So you can see number of atoms in one cell is 8. So now we get the number of atoms. Then we should know what is the mass of a single atom, because there are 8 atoms, and we know the for density we should also consider volume, and to calculate volume the lattice constant A is given. So first, mass of single atom, this can be calculated using this formula. The mass of the material and Avogadro's number, those are given, so you can use this formula to calculate mass of single atom. And then density is calculated as how many number of atoms in one unit cell, and mass of one atom divided by the size of the unit cell. So I have directly written it is in centimeter, and this is already in gram. So final answer is this. So correct option is B. So I hope everyone else also got the answer, and there is no confusion here. Okay. Let me check chat box also if someone. I don't think these answers are for this question. Okay. Okay, so this is the next question. This is on Bragg's diffraction. Bragg's diffraction for wave is used to study the separation between atomic planes. For planes separated by a distance d, nth Bragg's diffraction is given by n lambda equal to 2d sine theta. Here theta is the diffraction angle. So what is the maximum wavelength for which this diffraction condition can be observed from a crystal with an atomic separation of 0.6 nanometer? So again I will give 2 minutes for this question also. You can think about it and give me the answer.
Is the correct option B?
Yes, the option is 1.2 nanometer. What
Can I
about
ask a
the
doubt?
others?
Can I ask a doubt?
Yes.
In this question, it has been mentioned that the atomic separation is 0.6 nanometer. So we have to take small d as same as atomic separation. This is the question.
So the yes, for this question the atomic separation is only given. So it depends on the crystal structure also, so how Bragg's diffraction is observed. So for some planes there will be constructive interference, and for some planes, so we get certain planes for its crystal structure. But since no other option is given here, so you can consider the atomic separation for, because that's how the atoms are arranged, and basically the planes we consider, those are like imaginary, those are not real. So atomic separation is itself is the distance between the planes actually. I'm not getting any answers from the others also. Just please try to solve and give me the answer. Okay. So I hope you have also solved. Uh, so to determine the maximum wavelength, so we have this formula n lambda equal to 2d sine theta. So to get the maximum lambda, n should be 1, and that is the minimum value of n. And to get maximum for sine theta, it will be 1. So theta is 90 degree. So lambda is equal to 1.2 nanometer. So the correct answer is B. Okay. Okay. Let's go to the next question. So this question has three parts. So you have to solve for three parts. This is for BCC crystal, body centered cubic. So the density is given as 10.22 gram per centimeter cube, and the atomic mass is given. So you already know Avogadro's number. So in one question we have discussed. So what are the atomic concentration, that is in per centimeter cube? What is the lattice parameter or lattice constant A? and what is the atomic radius of this material or this atom. So try to solve it in parts, like it has 3 parts, and you can try first and then I will give the answer. So you have already solved one similar question, the density for diamond lattice. So what were the parameters given in that question there? You calculated the density. Density here is given already, and the atomic mass is given. So what other parameter that was given in that question, the last question for diamond lattice?
I think that is constant.
Yes. So here the lattice constant was given, atomic mass, and the density was to be calculated. So in this question, density is given, atomic mass is given. So you can calculate the lattice parameter, lattice constant A. So try to solve that first, and then you can calculate atomic concentration and atomic radius. Let me give you the diagram for BCC crystal structure also. It will be easier.
Option A.
Option A, okay. I have to check also. Yes. Yes, option A is correct. What about others? Like I'm getting answers for only one person. At least tell me the steps that you. That's how we should proceed for this question. I have already said that we should start with the from the lattice parameter, right? So first, what will be the number of atoms in one unit cell for BCC crystal? So there are 8 corner atoms, so the total contribution will be 1, and then there is one body centered atom, so number of atoms will be 2. Okay, next what we will calculate? What will be the atomic weight, what will be the weight for one atom, right? So mass of single atom we'll calculate by dividing atomic mass by Avogadro's number, and then density is already given, so that is as 10.22 gram per centimeter cube, and this is already in gram, so we will get A in centimeter. I think others can at least calculate now what will be A. Okay.
3.1 per angstrom. Meter.
3.1 for angstrom. Okay, in answer is given in meter here, so 3.147 to 10 to the power minus 10. So next so we know the lattice parameter and number of atoms in one unit cell, so we can calculate the atomic concentration. So how we will calculate? There are 2 atoms in a cube of volume A cube, so A we already calculated. So atomic concentration N will be 2 by A cube. So what will be the value? So N will be 6.4 into 10 to the power 22 per centimeter cube. Okay, I hope everyone got this answer. Okay. So the third part is atomic radius of molybdenum. So how we will calculate? So here one side of the cube is A, it is lattice parameter. So this is A and this side is A, so the diagonal will be root 2A, right? And this is root 2A and this is A, so this body diagonal, this will be root 3A. You can calculate it, right? Or you can calculate, if you consider this as this point as 0, 0, 0, this will be A 0, 0, and this point will be in x direction, it is 0, y direction A, and z direction A. So you can calculate that also using the formula for the distance between these 2 points, right? So this body diagonal will be root 3A. So you can see this figure, actually these atoms are not that far away, these are like touching each other, so this distance is root 3A. And what will be the relation between this distance, this body diagonal, and radius of these atoms? So that will be 4R equal to root 3A. So R, then twice R, then R, so that is equal to root 3A. So A we already know, so R we can calculate. So R will be 1.364 into 10 to the power minus 10 meter. I'll again wait for some time. If anybody has any doubt, then they can ask. Okay, I hope there is no doubt. Let's go to the next question. So in this question, determine the Miller indices for these two planes. So this was covered in one of the lectures, so you can tell me the answers. Probably you don't need the options also, you can tell it directly. Okay. The diagrams are visible clearly, right? Can
Option A
someone?
is correct.
Okay, option A. Okay. Yeah, option A is correct. What about others? Okay, 1 to 1 and 0 to 1. Okay. Okay, I got two answers, and others also, please. At least this question is easy. At least you should try and give me the answer. Okay, so how you calculate Miller indices? First, you determine what are the intercepts with the three axes, x, y, and z. So for this figure A, intercepts are 2, 1, 2, and then we take the reciprocal of the intercepts 1 by 2, 1 and 2, and then we multiply with integer to multiply 2 to get the integer value. So for this plane, it will be 1 to 1. Okay, and for this figure B, intercepts for with x-axis, so this plane is not crossing x-axis, so the intercept will be infinity. For y and z, it is a, so that is 1 in units of a, and then we invert the intercepts, so that will be 0, 1, 1. So the correct answer is a, 1 to 1 and 0, 1, 1. So I think you all know how to calculate Miller indices. In one of the lectures, it was covered that why Miller indices are actually important, and why we name these planes, and why we consider directions. So can someone tell me what was explained in that video, like why we care about these Miller indices and directions in crystal systems? You have watched the week 1 videos, right? So it was covered in the videos. My voice is audible, right?
Yeah.
Uh, is there any disturbance? Or you can. Am I audible?
Yes.
Okay, okay.
Yes.
So, what is the answer for why we actually care about Miller indices and directions in different planes? So, see, for different crystal structures, different planes will have different atomic density, right? For different material also. So, that will actually determine the properties of the material. So, sir has explained in the videos that the etching in 111 plane of silicon and 100 planes in silicon, so that properties are different based on the atomic density, right? So that is why we define these planes, and that that is useful to interpret the properties of different materials. I have one question on for silicon also, 111 plane and 100 plane. So there also I'll explain this. Okay. So next, go to the next question. Okay. So this is for angle between planes. So silicon 100 surface is etched using KOH. Etchant preferentially etches along 100 plane, then 111 plane. Find the angle between 100 silicon surface and 111 plane. So what will be the answer? Calculate this, and again I will give 2 minutes and then you can give me the answer. This was explained in the video also, if you can recall. So, but try to calculate it yourself and give the answer.
Option A,
Yes,
54.7 degree.
yes, option A is correct. Okay, what about others? It's 54.73 degree, that is correct, yes. So this is the answer. Um the angle between two planes, this is for cubic system, uh, HKL, and these two planes, the angle is given as cos phi equal to, using this formula, and you can calculate for H1 HKL value as 100 and 111, so the answer will be 54.7 degree. So now tell me why you think that this H and KOH etches silicon only in particular, like it etches more in a particular plane. So what do you think, what could be the reason? So etching red in silicon for 100 plane, that is more compared to 111 plane.
Is it due to atomic density along that plane?
Ye-
Higher in 100 than 111?
yes. So the atomic density in plane, so that is what I mentioned earlier, like why we uh, consider this Miller indices in different planes. So if I go back to, I have one figure for diamond lattice. So we go back to that. Okay. So 111 plane and so 111 plane will be this plane, right? And 100 plane will be this like the plane that is at the front. So atomic density for this plane is less. You can calculate this. You should try this also, like atomic density in different planes. So how you will calculate atomic density in different planes? So you will consider the area that, like you calculated the number of atoms per cell. So there you will calculate similar way, like number of atoms in one plane, right? You will consider only the area. Here you are considering the whole volume, like one atom, one corner atom is shared by 8 unit cells. So how you were determining this? You are dividing whole volume into 1 by 8. So like that you can determine the atomic density based on the area of the atom uh, and the shared area between two planes, right? So you can determine the atomic density in plane and you can divide by the area of the plane, and that's how you can determine the atomic density for silicon in 100 plane and 111 plane. So there are more numerous atoms in 111 plane. So that is why the etching rate in 111 plane uh, will be less compared to 100 plane, right?
You mean in 111 plane number of uh,
Atomic
atoms of
density
less?
that will be more, so that is why H rate will
Yeah.
be less.
Mm-hmm. Yeah, yeah, yeah.
So if you want, and I can we can discuss about atomic density in different planes for the next, in the next class also, but I think you can you'll be able to calculate by yourself. Okay. Okay. So this is the next question. Calculate the separation of two consecutive 111 planes in silicon, and silicon has a lattice constant of 5.43 angstrom. So calculate this and you can tell me the answer.
Option A.
Yes, option A. So how did you get to that answer? Can you please explain?
With the expression D equals small a divided by root h square plus k square plus l square, we can place the value and we can get the result.
Okay. packing density same as atomic density. Okay. Yes, like in case of planes, yeah, it is same for packing density. So you must have already calculated for different unit cell structures the packing density at different planes, right? Yeah. Okay, so this is the answer for this question. If someone has not calculated it, they can calculate. Okay. Okay, I hope this question is clear. So this formula is for cubic crystal structure. For others, the formulas are given in those textbook. You can check any textbook on crystal structures. You'll get those formulas, and uh, I usually don't remember any of these formulas because I can always refer to any book and then use these formulas. But for cubic crystal structure, this formula is easy and you can remember this formula. So, is there any question? Let me go back to this question. Okay, since you don't have any question, let me ask you one question. So, in this question, the angle between the planes for silicon. So, how we are getting this formula? Cos phi equal to this formula. How we are getting? Can anyone tell? We are trying to determine the angle between two planes, right? Can anyone tell?
I think in the three-dimensional coordinate geometry, firstly, that we have been used formula like x upon a plus y upon b plus z upon c equals to 1. So something like that we have been created the formula for plane. So in the similar fashion, we are creating the formula for the plane in crystallography. Then can get some similar results. I think from there we are getting this type of formula.
Yeah, so yeah, what you said is correct. That for planes also we can write the equation for planes. So this particular formula, this is for cubic crystal system. So what happens in cubic crystals, and the direction and the planes, those are orthogonal. What I mean by this, that 100 plane is orthogonal to 100 direction. Okay, it will be easier here. So this is a cubic crystal system. So 100 plane will be this front, this plane, right? And this is the 100 direction. So this plane and this direction is orthogonal. Now if we want to determine the angle between two planes, and if we can draw orthogonal to this plane. Like suppose we want to calculate the angle between this plane and this plane. So you can see my cursor, right? Or should I use a pointer or something?
The cursor is visible.
Okay, so suppose we want to determine this angle between this front plane and this plane. So how we can do that? We can draw orthogonal, like a perpendicular line from these two planes, and we can also calculate the angle between those two orthogonal vectors, right? The property of cubic crystal system is that these two the direction and the planes are orthogonal. So we use this property here. We know how to calculate the angle between two vectors, right? A dot b is equal to ab cos theta. So that is actually the formula that is being used here. So because these planes and the directions are perpendicular, so we are calculating the angle between these directions. So that is how we are actually, that is why actually we are using this formula. Cos theta is equal to a dot b divided by mode of a and mode of b. So so this formula is for this kind of system where the planes and directions are orthogonal. I hope it is clear, right? Okay, since there are no questions, then okay. I already had that answer. So solve this question. I will not solve this question because I have already discussed some of the questions, and these you can solve based on this. The question is, in silicon the lattice constant is 5.43 angstrom. So consider the atoms as a hard sphere and calculate the radius of silicon atom. Determine the density of silicon atoms in terms of centimeter cube, and use Avogadro's number to find the density of silicon. I think you already know these values, like what is the density of silicon atom in centimeter cube, what is the atomic density of silicon, and what is the radius of silicon atom. But use the formulas, those I have already discussed, and calculate this again. Tell me the answers. Here I have not given the options. I think you already know the answers, so just calculate and tell me the answers. Again, this is the crystal structure for silicon, that is diamond lattice.
Part B, determine the density of silicon atom in atoms per centimeter cube.
Yeah, it is per centimeter cube. Sorry for this.
Okay.
let me give you one clue also. Here, the distance between, so in case of silicon, it is the it is a diamond structure, and in diamond structure, basically two FCC lattice, face centered cubic lattice, are interpenetrated and shifted by 1/4 of the body diagonal. So the distance between these two atoms, this is 1/4 of the body diagonal, and you already know the what is the body diagonal for this kind of lattice, right? So you can use that concept to determine the radius of silicon atom. So what is the body diagonal in diamond lattice? If one side is A, then what will be the body diagonal?
Body diagonal is root 3.
Yes. So this is root 3a, and this distance is 1/4 of that. So now you can calculate the radius of silicon atom. Consider hard sphere model. So that means these two atoms are touching each other. So that distance will be equal to 2r, which will be equal to 1/4 of the body diagonal. So now tell me the radius of silicon atom. So this one, this is already answered. The distance between A and B. What is the distance between A and C? So that is root 3a by 4.
One 1.17 angstrom.
Yes. So everybody got the answer? If one corner atom is vacuum is vacuum due to defect packing density of diamond Okay, so if one corner atom is vacant, then how we will calculate the number of atoms in um, one unit cell? So we will consider 1 by 8 into 7, right? So that is how you will calculate. Okay, I'll discuss that first. Let me know if you already got the answer. R equal to 1.176 angstrom.
Will the density be 1825.46 gram per centimeter cube and the concentration be 4.99 into 10 to the power 28 per centimeter cube?
Uh, so, how did you calculate? I don't think that is the correct answer. Okay. R you already got, right? 1.176 angstrom.
Yes.
Okay. So, the density of silicon atom. Okay. So number of atoms per cell is 8, right? This is correct. Good.
Yes.
And then atomic concentration, that will be 8 by a cube.
Yep.
Okay. So then n should be 5 into 10 to the power 22 per centimeter cube. So please check the calculation again. Let me do again also.
Yeah, I got it. I got it.
Okay. So what was the mistake with the
Uh,
units?
yeah, yeah.
Yeah.
The
Okay.
units.
So generally we write n or concentration of electrons or holes in per centimeter cube, so you should always be careful. So generally
Alright.
when you said that it is 28, so I realized that you must have calculated using different unit.
Alright. And will the density be 1825.46 gram per centimeter cube?
No, first the so why I'm giving you this question, we have already discussed for BCC crystal, right? But this is particularly for silicon, and these values you can always look, you can always check a textbook, or you can search it in internet. But you should remember this, like the lattice constant for silicon is 5.43 angstrom, and density is 2.3 gram per centimeter cube around. So maybe you have done some mistakes in calculation, so you can check again. So what is the atomic weight of silicon you have considered?
22.
Is it 22? You can check and you can correct it.
Yeah, sure.
So did you get the answer? That's 2.33 gram per centimeter cube. everybody got the answers? Radius of silicon atom, density of silicon atom.
Do we have other models other than hard sphere model to calculate these numbers, or is it the only? And how accurate is these models? Are these models?
So, okay, I'm not exactly sure if there is other model
Yeah.
also. And
I have also not come across any other model. That's why I wonder. Is, and how accurate is this model?
so, when if I
Yeah.
go back to this slide.
Hmm. Yeah.
So the exactly like how the separation is between these two atoms, between like inside the unit cell, how it is can we visualize it? Because this distance, even if these two atoms are not touching each other, so that distance will
Mm-hmm.
be very small, right? So this is in
Right,
angstroms.
right.
So
Mm-hmm. So I don't think that will
any
matter much.
characterization method also, it will be very difficult to
Mm-hmm.
determine the distance. So
Mm-hmm.
for calculation, this is what we are considering. And in I have not also come across any other method like how we calculate the atomic density and other parameters.
Mm-hmm.
Yeah.
Okay, okay.
Okay, I hope everybody got these answers right. Density is 2.33 gram per centimeter cube. Atomic concentration is 5 into 10 to the power 22 per centimeter cube, and radius is 1.176 angstrom. Okay. So you should remember these values at least for silicon. So here n is equal to 5 into 10 to the power 22 per centimeter cube. So do you know about doping? Like since all of you are PG or PhD level student, you know about doping, right? Doping in semiconductor. So in silicon, we usually dope with pentavalent or trivalent atoms like phosphorus or boron. So uh, usually what is the doping concentration? Like typically what is the value? Give me, tell me like in 10 to the power in some term, like what is the typical value for doping. So you have already solved questions of p-n junction diode or MOSFET. So what we typically take as doping concentration, p-type doping or n-type doping.
In the order of 10 to power 20 per centimeter cube.
Okay, 10 to the power 20 also, that will be
Uh,
highly doped, right?
yeah, definitely.
uh,
Almost 1% impurity will be there.
Yes, so 16, 17, those are 10 to the power 16 or 17, those are typical values in centimeter cube again. The unit is important. Um, so the density of silicon is 5 into 10 to the power 22 per centimeter cube. So you can calculate what is the percentage or how many atoms are there, the dopant atoms are there. So if you know the other parameters like dimensions and volume, the other parameters, and for silicon it cannot exceed, it definitely cannot exceed 5 into 10 to the power 22. So when you look at this number, so you should always be careful and you should think like, okay, so what it implies 5 into 10 to the power 2, and what doping concentration of 10 to the power 16 implies, whether it is a lightly doped semiconductor or highly doped semiconductor or degenerate semiconductor, those things. Okay.
Uh, if we will dope this silicon semiconductor with some element whose size is smaller than silicon,
Okay.
even then also we cannot go past this number of 5 into 10 to the power 22, because that way volume is fixed for silicon, and then we are reducing the size of atom. Then
Okay.
shouldn't it be a
But
little bit maybe?
so
Then
see,
that way it will not called as doping. I understand. Yeah.
uh, so the bond, ultimately the atoms will go to these
Uh,
lattice sites.
the,
So
right, right.
if the atoms are not in the lattice sites, so that will not
Then it will not
contribute
be
much.
called as
So those will
right,
be
right.
defects, right? So we want
Hmm.
dopant, not defects. So
You
if
and dopant, yeah, exactly.
Huh. So if
Hmm.
those are in lattice sites, so those will contribute to the covalent bond. Like there will be one missing electron or there will be an extra electron. So um I'm not sure what the size of the atoms will change the how the size of the atoms will change the properties, but ultimately for doping number of atoms and number of um, lattice sites, or that is important. Okay.
Yeah, that atom should replace
Replace
this
this.
silicon atom. Yeah.
Then only there will be extra electron and extra hole, electron
Whole.
and hole pair. Yeah.
Hmm.
Okay. Anybody has other questions? I don't have more questions. We still have time. So someone has asked one question. Okay. So if one corner atom is vacant due to defect packing density of diamond, so you can use this formula, but generally packing density we calculate for crystal structure. So we don't consider about the defects. So when we consider the whole material, then there will obviously be defect and the density will not be exactly the same. But for single crystal, although we can calculate, like instead of 8 corners that will be 7, but it will not be I mean there will be no significance, there is no much significance for that. So if you want to know mathematically we can calculate, but for crystal structure uh, it is the crystal structure for diamond, right? So in real material there will be defect, and so the atomic density and other parameters will be might be different, but uh, for crystal structure we will use these formulas. Any other question? So I'll stop sharing now this PPT. So you have already gone through the week 1 lecture videos, right? Textbook to refer, know the basics of the so this course is semiconductor device modeling and simulation. So there if you look at the syllabus, so let me share the screen again. So this is the syllabus, right? Basically, week one actually, some of the concepts those were touched. Those will be discussed in some of the later lectures also. So you will anyway go through those. But for the first for the first few weeks, actually, these are basics of semiconductor devices. Modeling part will come mostly at the later part. So the books and references are given here, so you can go through this for semiconductor basics of semiconductor devices, Streetman and Z. These two books, those you can follow, and for the course. Uh, so this third book that is mainly being used, so that was mentioned in the video also. So this book you can also uh, go through this book also, but for the basics, Streetman and Z, these two books are also good, so you can go through those. Okay. So in week 2, it will be reciprocal space, doping, band structure, and effective mass. So yes, these topics you can find in these books. So all of you are registering for examination, or so how many of you have registered for examination for this course also? Okay. Okay, so only one.
I've been registered too.
You have registered? Okay, two. Okay.
Yes.
Okay. Okay, three. So all of you, all three of you are PG student or PhD, right? Okay. So PhD and PG. Okay. So you already know the basics for this course. If your background is electronics, then you already know the basics of this for this course. So I hope you are going through the assignment questions also, and those you can solve by yourself. See, the idea for this session is that so you get enough practice so that you can solve the assignment questions also. So if you have any doubts, then you can ask in these live sessions also. Some other live sessions will be covered by some other team members. So you can ask the doubts also, but we cannot directly give you the answers for the assignment. But if the concepts are not clear, I would suggest that you discuss uh, during the live session and get enough practice for these sessions. Okay. So there is one assignment 0, so week 0 question also. Have you tried that?
Yes.
And you got the answers correct, right?
Yes, most of these.
Most of this. Okay. So uh, what were the wrong answers? Like, where did you struggle?
Can't remember. All those are wrong answers. Basically, I updated it and I got the right answers.
Okay, I'll share my screen also. Okay, so this is week 0, assignment 0. Okay. Which component function as a one-way current valve? So what is the answer?
Diode.
Okay. And others also please respond. Okay, what happens to the width of the depletion region during forward biasing of PN junction? Uh,
It decreases.
it decreases.
Decreases.
Okay. What is the electron drift velocity if electron mobility in a semiconductor is 1800 centimeter square per volt second and the applied electric field is 400 volt per centimeter?
7.2 into 10 to the power 5 centimeter per second.
Okay, how you calculate the drift velocity? What is the formula for drift velocity?
Mu dot E.
Mu dot T. So mobility and applied electric field.
Yeah.
Okay. Okay, for the next question, I want someone else to answer this. Okay, choose the correct one according to their conductivity. So, among insulator, conductor, and semiconductor, which one has the highest conductivity? Conductor has the highest conductivity, right?
D, ma'am.
D. Yeah. So, if conductor has very good conductivity, why we don't use conductors mostly in our circuits? Why we consider why this course is semiconductor device modeling and simulation? Like why semiconductor is most useful?
Because it has both the properties of semiconductor and insulators based on its doping level. We can
Yes,
use it in both the ways.
yes, we can basically control the current. That is what we want
Control
in.
the
Uh,
flow of current.
yes, that is what we want in our devices. Like we want to control the flow of current. Okay. What is the primary charge carrier in intrinsic semiconductor?
A, ma'am.
A.
Holes, current and holes. I mean, electrons and holes.
Yes. So how in intrinsic semiconductor charge is generated, how electrons and holes are generated?
In this question, I was trapped. Can you please elaborate how holes participate in conduction in case of intrinsic semiconductor?
Okay, so see in intrinsic semiconductor, electrons and holes are created in pairs, right? Uh,
Even
these
though this is the correct answer, but
uh,
I got trapped. Do we have any examples like? I can't remember it.
so see these electrons will occupy, this will be in the conduction band, right? There will be some electrons and mostly the conduction band will free. So electrons has a negative charge associated with it and it can move freely in the conduction band, so that will give rise to current. That is for electrons. And for holes, it is the missing electrons in the valence band. There are many missing electrons. I consider missing electrons many vacant state in conduction band also, but holes are the vacant electron, like these are the places where electrons were supposed to be there. So these holes are in valence band, right? So when there is no when there is an empty state, empty space in valence band, so there are many electrons in valence band. So those electrons will move to this valent like empty state, empty space, and that will lead to actually a flow of current. So holes are considered, that is why holes are considered as a positive charge. So there are many electrons in valence band, so you cannot keep track of all of the electrons, so you can keep track of the holes. If the valence band is completely filled, so electrons will not be able to move, because there are holes. The holes will actually move. Actually the electrons will move, but it seems like the holes are moving, so that will give rise to current. So for intrinsic semiconductors, the current comes from both the electrons and holes. And in extrinsic semiconductor, depending on whether it is a p-type semiconductor or n-type semiconductor, so there will be majority concept of majority carriers. Either electrons will be the majority carriers or the holes. So there we mainly consider the charge carriers as the majority carriers. So basically holes we consider for valence band. Okay.
I think in the intrinsic semiconductor, since we do not have free charge carriers, so let us consider once we raise the temperature, then electron and holes both will create it.
Yes.
So can we say in that perspective, we can say that the electron and holes both are the charge carrier in case of intrinsic semiconductor?
Electrons and holes are created in pairs, so
Yeah.
in
So
thermionic emission, yes.
yeah. So
But current will so how current will be generated if those carriers will move actually, right? So the electrons in conduction band also can move, and the holes in valence band also can move, so that give rise to current. So that is why the charge carrier we are considering as electrons and hole.
all right.
Okay.
Sure.
I think Divyanshu, that you have mentioned that there is no carriers in intrinsic semiconductor. That is not right.
Uh,
You have said
I said there are
something,
no free charge carriers.
but it is
free
there. I think the
free
numbers
charge
are very small.
free charge carrier at absolute zero temperature, right? If
Right.
the temperature is a little bit high, not 0 Kelvin, so there will be some free charge. There will be some electrons and holes pair because of this
So I
thermionic
think there
emission.
will not be individual free charge carriers like only electrons will there or only holes will there in case of intrinsic semiconductor. If there is presence, then both of these two will present at any temperature.
Yes, both of these will be present. Yes, so that is n equal to p. So that is the formula for intrinsic semiconductor.
All right.
Okay, so what is time is already 50. What is the purpose of transistor in electronic circuit?
Control the current flow.
Control the current flow. Yes. This is in similar line with the first question, like diode and transistors. Okay. Which semiconductor device emits light when forward biased?
LED.
LED.
LED. Okay. So for LEDs, what material we use generally? I mentioned in the at the beginning of the class, right? What kind of what should be the band gap to emit light?
Gallium arsenide.
Gallium arsenide is, so we can use direct band gap material, so that will emit light, and the wavelength, the band gap, so that the band gap energy that should lie in the frequency the energy of the light. So the light that will emit, that will have the energy or equal to the band gap, right? So okay, yeah, so that is why we want a material. Suppose we want a blue LED, so the wavelength should be the wavelength should the wavelength will have a relation with the band gap. So do you know how the
I think the relation is something like electron band gap equal 1.24 nanometer divided by wavelength or 1.24 micrometer divided by wavelength.
uh,
Can't remember it properly, but the expression is something like that. Band gap equals 1.24 uh, divided by
divided by
lambda wavelength.
lambda, yeah, 1.24 in micrometer, so and
Right?
1240 in nanometer. So that comes from the Planck's constant, E equal to hc by lambda. So if you multiply h and c, so that will give 1.24 in micrometer or 1240 in nanometer. So yeah, for LEDs we use direct band gap semiconductors. Okay, in a semiconductor crystal at 0 Kelvin, how are electrons arranged in the valence band and the conduction band? So I think we have already discussed this. What will be the answer for this question?
Option B.
Valence band is filled and conduction band is empty. So there is no free electron in the conduction band, and there are no holes in the valence band.
Valence band.
What is the purpose of introducing impurity or doping in semiconductors?
To modify electrical conductivity.
Yes. Yeah. That is where the usefulness of semiconductor comes, as some of you have already mentioned, right? So we can dope semiconductors and we can control the conductivity and control the current flow. Okay. Which semiconductor material is commonly used in integrated circuits due to its abundance and versatility?
Option B.
Yes, we silicon. Okay, that's everyone answer. Okay. Okay. Is there any more doubt? It's already 4:58. If there is any doubt, then you can ask. Okay, so today it is almost 2 hours. So um, and we are using the same Google Meet link. So I think this time limitation is not yet applied to person's email ID, and we can continue with one Google Meet link. But today I almost forgot to share the second Google Meet link. So please remind me in coming sessions. Again, I will not take all the live sessions, but if I take the live sessions, then please remind me to share the second link also in case this first link does not work. Okay, we
Can I ask a doubt? Uh,
yes.
if we can do that. So when we fabricate, like let us consider we are fabricating a semiconductor in such a way that there is a silicon layer and over which there is a silicon dioxide layer. So is there any way by which we can change the interlayer distance between the silicon dioxide and silicon, bulk silicon?
So what do you mean by interlayer distance? Like the
Uh,
thickness of the
uh,
SiO2 layer?
the distance between SiO2 layer and the bulk silicon. Basically, this question arises because I do simulation
Uh-huh.
on two-dimensional materials.
Okay.
So, in case of two-dimensional material, we have one layer up to which there is another layer. So, in case of simulation, I have a type of doubt in choosing the interlayer distance between those two layers of semiconductor. So, I think the similar phenomena will be applicable on the bulk semiconductor. So, is there any? Basically, I want to mention that I do not have that much idea about the experimental cases. So, is there any way through which we can change the interlayer distance, the distance between bulk silicon and SiO2?
So you are asking interlayer distance, so I'm guessing you are saying the bond length between silicon and oxygen.
No, basically, let us consider that we are having a silicon layer and there are some free dangling bonds,
Mm-hmm.
and then there will be a SiO2 layer over which there will be a SiO2 layer, right?
Yes.
So the distance between SiO2 layer and the bulk silicon.
So
Let
you are
us
saying
consider
the thickness of SiO2.
there should be some space between. I want to ask some more question that is there bonding between SiO2 layer and the bulk Si? Is there any
So
bonding?
the top surface, the top silicon atoms,
All right,
those will bond with the oxygen atom, right, to
all right,
form the SiO2. So there will be certain bond length. So I don't
all right.
remember the bond length.
All
So
right, so that particular phenomena will not be applicable over there. I thought there is different SiO2 layer and there is different silicon layer. Like that happens in case of two-dimensional materials that I do simulate. I think there is a difference between these two situations.
I think so because
Basically,
you
in the
can
fabric.
control the thickness of the SiO2 layer, and you know the thickness of bulk silicon. You can control that thickness also, but
All right,
between silicon and oxygen, how exactly, like you, yeah, I don't think can be controlled, that there will be certain bond length between silicon and oxygen.
all
So
right,
you can look these problems. I think this kind of problems will be available uh, in textbook and internet also. Like what is the bond length in case of silicon structure, and what is the bond length in SiO2 for SiO2 also. So that bond length, yeah, for 2D material, I'm not sure how it is calculated, the distance.
all right, sure.
Okay. So yeah, it's almost 5 o'clock. So I hope you learned something in this session, and this session was useful. So let me conclude this session, and uh, this you can. I request you to utilize this live session. If you have any doubts, you can ask in the later sessions also. And since the registration for this course, number of students registers, that number is very large, but I can see only few people here. So if you have any doubt, you can unmute yourself and ask directly. If the number of participants are more, then it is difficult to actually uh, like clarify doubts. So in that case, you can write. Okay, in that case, you can write in the chat box. But for this kind of session, I think it will be useful if you directly unmute and ask questions. Okay. Okay. Thank you, everyone, and see you in the next sessions.
Thank you.
Thank you, ma'am.
Okay.
Thank you, ma'am.
I'm leaving this call.